Hello. So let's do an overview of the exam topics that we'll be covering. You are allowed a cheat sheet, one page front and back, like the first test. Submit your cheat sheet with your test. My first thing, and very important, is to thoroughly understand matrix multiplication. Now, two things I've been bringing out quite a bit. The jth column of the product of two matrices is equal to the first matrix times the jth column of the second matrix. In particular, if the jth column of the second matrix is one of the columns of the identity matrix, for instance, if the jth column of the second matrix is the jth column of the identity matrix, then this product will simply be the jth column of the first matrix. You can verify that. The ith row of the product is the ith row of the first matrix times the second matrix. Now, very similar. If the ith row of the first matrix is the, say that's the third row of the identity matrix, then this product will pick out the third row of the second matrix. These two are related by transpose. You can prove one by taking the transpose of the other one. Now, I may ask you to calculate a single entry from the product of two large matrices. So you should be able to, if I tell you I want the entry in the fourth row and seventh column, you should be able to give me that single entry without doing the entire product. And you should be able to give me the formula for that. Okay? Find the homogeneous and general solutions to a set of linear equations. I express the set of homogeneous solutions as the span or linear combination of a set of vectors. This is what he calls vector form. Let's see if we can find an example. All right, well, here is a solution set in vector form. It's the linear combination of vectors. Actually, it's the linear combination of one vector. It can also be thought of as the span of this single vector. Now, we can also find the particular solution. If we look for a particular solution up here somewhere, I'm sure we can find one. All right, here we go. This part is a homogeneous solution. It's a linear combination of two vectors, and so it's the span of these two vectors. This is the particular solution. This is a solution to an inhomogeneous system. Right? So you should know how to express solutions this way, and you could write this homogeneous part simply as the span of these two vectors. Span is denoted by square brackets. So square brackets, this vector, comma, this vector, is equivalent to this homogeneous solution. Okay. Where are we? Express this. All right, so we did that. Spanning set's basis and dimension. Be able to tell whether a given set of vectors is a basis for a given subspace. All right. First of all, it needs to span the subspace. Second of all, it has to, and well, I should say, first of all, the vectors must be contained in the subspace. Second of all, they must span the subspace. And third of all, they must be linearly independent. We need to check those three things. So given a spanning set of a subspace, find the basis. If that's the spanning set, you've already got that. It's contained in the subspace, and it spans the subspace. You'll need to find a linearly independent subset. So you should know how to do that. Basically, you can throw out vectors one by one until you get something linearly independent. Remember that a basis is a minimal spanning set. You can't take any vector out of the basis and still have it span. On the other hand, it's a maximal linearly independent set. If you add any vector to a basis, it cannot be linearly independent anymore. So know how to tell if a vector is in the span of a set of vectors. Basically, you're going to solve an inhomogeneous vector equation. Okay, next, find the null space and range space for a matrix. Null space is just another name for the set of homogeneous solutions. Please make that connection. The range space is the column space. It's the span of the columns. Okay. So I might ask you to find a basis for the range space. So how would you do that? Well, just find a set of linearly independent columns. Right? So the dimension of the range space plus the dimension of the null space is the number of columns of the matrix. So that's something you remember. How do you see that? Well, let's see if we can find an example. Well, Here we have a matrix, augmented matrix, that we reduced to reduced row echelon form. Okay. And we get the solution like this. In this case, we have a particular solution, and this is the null space. Now, what does this null space actually mean? Remember that we can think of this equation here, or we can think of this matrix as representing an equation. Let me grab this and we can show you this. Let me move it down here. Okay. So we'll insert the screen clipping. You got this. So what are we doing here? We are actually solving for the vector equation 2, 0, 0. Well, what you're trying to solve is 2, 6, 1, 2, 0, 3, 1, 4, 0, 3, 1, 2 times x, y, z, w is equal to 5, 1, 5. Sorry, I should make that a column vector because that's how it turns out. 5, 1, 5. Now, how do you interpret this system of equations? You can write these out as 3 algebraic equations. You can also write this as 2, 0, 0 times x plus 6, 3, 3 times y plus 1, 1, 1 times z plus 2, 4, 2 times w is equal to 5, 1, 5. Okay. All right. So what does that mean? That means that I'm trying to solve for a linear combination of these vectors to get this vector. All right. So this is a linear combination of the column vectors. Okay. Right now, so let's look at the solution. The solution was, he has it right here. Well, he wrote x1, x2, x3, x4 instead of what I wrote. So let me do this here. Now this here is the inhomogeneous solution. This is the homogeneous solution because it's multiplied by x3. Let me write down this homogeneous solution. 1/2 minus 1/3, 1, 0. So let's consider the case where x, y, z, w is equal to 1/2, what was it, 1/2 minus 1/3, and then 1 and 0. Right. Now, we know that this is a homogeneous solution. And what that means is that 1/2 times the first vector minus 1/3 times the second vector plus 1 times the third vector plus 0 times the fourth vector is equal to 0. Okay. So this gives me a non-trivial linear combination of these basis vectors. Right? This gives me 1/2 2, 0, 0 minus 1/3, 6, 3, 3, and you can verify this. Then plus 1 times 1, 1, 1 is equal to 0, 0, 0. Okay? Okay? So the dimension of the null space is the number of linear combinations of row vectors, number of independent linear combinations of row vectors that give me a homogeneous solution. So the dimension is equal to the number of independent linear combinations of the column vectors. that gives 0. That see, I said number of. I shouldn't say number. I should say number of different. I should say different. Number of different linear combinations of column vectors that gives 0. Okay, because this is a linear dependence relation, right? This is a linear dependence relation. So this is the number of linear dependencies of the column vectors. Each time I get a homogeneous solution, I can get a different linear dependence relation of the columns. Okay, so that means I have the number of linear column vectors, and I subtract the number of linear dependencies those are the number of vectors I can remove and still form a basis. So that's going to be equal to the number of linearly independent columns. All right? Each time I get a linear dependence relation, I can subtract one vector. For instance, in this case, I can subtract this. I can subtract 1, 1, 1 because it's a linear combination of the other two. Okay, so the number of column vectors is the number of columns minus, and then this is the dimension of the null space, and that gives me the dimension of the row space, dimension of the column space. Okay. Or in other words, the number of columns is equal to the dimension of the null space plus the dimension of the column space. All right, so that's another way of looking at the null space. All right, let's go back to our set here. Okay, so that's one thing you should remember. Okay, and try to understand why that's true. Okay, determinants. Understand how row operations change determinants. What does row exchange do to the determinant of a matrix? If you multiply one row, what does that do to the determinant of the matrix? If you multiply one row and add to an existing row, what does that do to the determinant of a matrix? You can find the answers in the book. You should know the 2 by 2 matrix determinant formula. I would not memorize the 3 by 3. I don't know the 3 by 3 determinant formula. It's one of those peculiarities. All right. You should also know how to find the determinant of special matrices. If you have an upper or lower triangular matrix that has all zeros below or all zeros above the diagonal, then the determinant is the product of the diagonal entries. Or you can have a block diagonal matrix. I had an example up here that I wrote out. Here I have a matrix that's 1, 3, 2, 4 in the top left block, 0, 0, 0, 0 in this block, 0, 0, 0 in this block, 4, 9, 7, 1 in this block. You can treat these blocks as if they were diagonal entries. So the determinant of this matrix is the product of the determinant of the determinants of the diagonal blocks. Okay? So you can break down a bigger matrix sometimes into smaller matrices. You should also know the relationship between determinant and area. Here I have two vectors, v1 and v2, and I take the matrix whose columns are v1 and v2. The determinant of that matrix is the area of this parallelogram. Similarly with 3 vectors. If you have 3 vectors in 3 space, it's not going to be an area, it's going to be a volume. Volume of the box determined by those 3 vectors. Okay? All right. So linear transformations. Given a linear map on vectors or polynomials, find the matrix corresponding to the map with respect to a given basis. So I wrote out a problem here. Let's take this linear transformation. T takes a plus bx plus cx squared to this polynomial here. So this is in degree 2 polynomials. Okay. So this is telling me uniquely the image of each polynomial. So give the matrix of this transformation, first with respect to the standard basis, which is 1x x squared, and b with respect to the basis 1 plus x, 1 minus x, and x squared. Let me zoom in a little bit. I think okay. All right, and let's go out here. Okay. All right, okay. Now, in the standard basis, so this should be, okay. So in the standard basis, I would identify a plus b plus c x squared is a, b, c in the standard basis. I'll call the standard basis E. Okay. So the point is, find out what the transformation does to each basis vector in this representation. What does it map 1, 0, 0 to? Well, plug in 1, 0, 0 for a, b, c, and you'll get that 1, 0, 0 maps to 0, 1, 1. Just follow the A's. Okay. What does 0, 1, 0 map to? Similarly, plug in 0 for A, 1 for B, 0 for C. Get out your result. If you plug in 1 for B, let's see what happens. The only B is here. So the result is 1, 0, 0. Again, in the standard basis. I can put E's here just to make things clear. And similarly for the third one, right? So the matrix of the transformation is simply the matrix whose columns are the images of these identity vectors. Okay. All right, so let's look at the matrix now with respect to different bases. 1 plus x, 1 minus x, and x squared. Right. Now, in basis, so this is my basis B. Now, in basis B, this first vector has the representation 1, 0, 0, because it's the first vector in my basis. So in basis B, that's its representation. Okay. So I can write it as a polynomial, but in my standard basis, that's 1, 1, 0. Now, what does T map this to? All right. We can just multiply by the matrix I found in the E basis, and I get this. And so this is in the E basis now. Let me write that as a polynomial. I can write it as 1 plus x squared, and this is just, if I write this in the B basis, this is 1, 0, 1 in the B basis. You can see up here, it's 1 plus 0 plus 1. Okay. In this simple case, you can just see that by inspection. Right. So, what does the second basis vector in basis B map to? 0, 1, 0. What's 0, 1, 0? In polynomial form, it's 1 minus x. In standard basis, it's 1 minus 1, 0. Under T, that maps to, I use my matrix representation, right? This is rep E of T, and this is times 1 minus 1, 0. It maps to this vector in the E representation. To transfer it back to B, I need to express it as a polynomial. Minus 1 minus x plus x squared. Okay, this is just minus, you see, it's just minus this vector plus this vector. So it's 0 minus 1 times the second basis vector plus 1 times the third basis vector. Let's do the last one. Last one. 0, 0, 1, that's x squared. Well, in the E basis, it looks the same. What does that map to? Well, it maps under T. Again, this is the representation with respect to the E basis of T. And then this is the vector with respect to E basis. So this is the result in the E basis. I write this out as a polynomial, and I express that polynomial as a B basis. Okay. So what's my representation? So the representation with respect to B of T, well, I take the images of the three basis vectors in the B basis, right? Image of 1, 0, 0 in the B basis was, it's off the page, I'll have to shrink a little bit. It looks like it's 1, 0, 1. Okay, so that would be the first one, 1, 0, 1 right here. Okay, So this is 1, 0, 1. Image of the second one, right here, 0, minus 1, 1. Let's go back and find it. Okay, and the third one should be right here, 1, 0, minus 1. Okay, so express the matrix in an alternative basis. Okay, let's see what else we have here. Determine whether a linear map is isomorphism. Isomorphism is actually the same thing as invertible. Okay, and that's the same thing as the null space is 0. Okay. And so it's the same thing as only a trivial homogeneous solution. Trivial. Right? Next, find the orthogonal projection of a vector onto another vector. Okay. There's a formula, but there's also geometrical understanding, which you should have. It's easy to draw the picture. I drew it down here. Okay. So if I want the orthogonal projection of W onto V, okay, what do I do? Well, here I draw W, here I draw V. I drop the perpendicular, basically. Okay, the orthogonal projection is this red vector here. Okay. Now, if you use trigonometry, you can see the length of this red vector is the length of W times cos theta. Right. Now, what's cos theta? You use this Cauchy-Schwarz inequality to get cos theta. W dot V over the length of W times the length of V. Okay. But I'm multiplying that by the length of W. So the length of the projection is W dot V over the length of V. So this is the projection onto V of W. Okay. So that's the length of this projection. So that means instead of writing vector, let me write proj of V on W. So we'll take this and we'll erase what I wrote here. Okay. The projection is the part that lies in the vector. So this is the projection onto V of W. And you can see it's parallel to V. It should be parallel to V. So I just take this length times the unit vector in the direction of V. So maybe I can see that. So this is the length. And then this is the unit vector. Okay, so I just get this result. It's the inner product divided by the squared length times the vector. Notice there are two factors of V in the numerator, two factors of V in the denominator. Okay, so the magnitude of V is going to cancel out. But what's going to matter is the direction between V and W. Okay, right. So this means I can call this the residual. The residual is equal to W minus the projection onto V of W. And this vector is perpendicular to V. Okay. You actually have the triangle inequality, which is something you might think about proving. The length of this red vector squared plus the length of this green vector squared is equal to the length of W squared. And you can actually work that out just using algebra. Okay. What's the length of this vector here? Well, this is a number, so it comes out. The length of this is the square root of V dot V. So if you square that, you'll see what you get. And then you can square this one. It's a little bit complicated, but you can take this formula down here and square it. And you'll see that terms cancel out, and you'll end up with the length of W squared. That might be a fun exercise to do. All right. So I should say You can show this, show that the length of the projection onto V of W squared plus the length of the residual squared is equal to the length of W squared. Okay, and residual is this second vector here. All right, and it should be lightweight because it's perpendicular. Okay, let's look at what's next. Find the orthogonal projection of a vector onto a given subspace. Where's my mouse? Okay, here we go. All right, now here you probably just need to write down the formula. Okay. Subspaces. Be able to tell whether two subspaces are disjoint except for the zero vector. So think about how you would do that. If you have two subspaces, you can get a basis for each subspace and see if concatenate those two bases together, and if they're linearly independent, then the two subspaces are disjoint except for the zero vector, because there's no relationship that relates a vector in one subspace as a linear combination of the vectors in the other subspace. Okay, next, be able to determine whether two subspaces are complementary subspaces. So look back at the definition of complementary. Those two subspaces must intersect in the zero vector, and the sum of the dimensions must be equal to the dimension of the entire space. Right, be able to tell whether a vector space is the direct sum of subspaces. Okay. So here you have two subspaces. Basically, if you have two subspaces that are complementary, that means the vector space is the direct sum of the two subspaces. But you can also have the direct sum of more subspaces. You can have the direct sum of 3, 4, 5 subspaces, and more than that. The point is, the subspaces must be pairwise disjoint except for the zero vector. They must intersect pairwise in the zero vector, and they must also, the sum of the dimensions must also be the dimension of the vector space. We can go back and see if we can find that in the book. Actually, I think I'm going to need to correct myself. Here you have the subspaces of a vector space. The sum, which is denoted this way, is the span of the union. So in other words, you take a basis of W1, basis of W2, blah, 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 basis of WK, and take that as your spanning set. Okay. Now, if you have bases for these different ones, they may, when you put them together, they may not be a basis. But when they do form a basis, then we say that this is a direct sum. I said that the subspaces have to be pairwise, pairwise intersect in the zero vector. Apparently that's not enough. But it is true that the concatenated basis must be linearly independent. And then if the concatenated basis is linearly independent, then this sum is a direct sum. Right, so if we go back here. So that's how you would tell whether a vector space is the direct sum of subspaces. Get a basis for each one of the subspaces, put them together, see if that's a basis of the entire space, and see if the number of vectors adds up. Okay. So find the basis for a sum of subspaces. Right. So as I said, you may take a sum of subspaces and take a basis of 1 and a basis of 2. That may not be a basis of the combined, of the sum of the two subspaces. So you'd have to do the same thing. You just solve the homogeneous equation and then find a linear dependence relation, and then you can remove the vectors one by one. Right, find the orthogonal complement of a given subspace. So what you want to do is you want to find a basis of the entire space, which includes a basis of the subspace, and the other vectors are all orthogonal to that subspace, perpendicular. All right. Almost done. Similarity. You should be able to find eigenvalues of 2 by 2 and simple 3 by 3 matrices. Again, I don't really see a lot of purpose in your being able to do the long algebraic computation with 3 by 3 matrices. But you should be able to see some simplifications if there are simplifications. Like I said, if you have lower triangular or block diagonal or something like that. right, given the eigenvalues of a 3 by 3 matrix, express M as PDP inverse, where D is a diagonal matrix. Remember that D will have the eigenvectors on the diagonal, and P will be the matrix whose columns are the eigenvectors. No, you may not have enough eigenvectors, then the matrix is not diagonalizable. We have an example of the matrix 0, 0, 1, 0, which has eigenvalues 0, multiplicity 2, but it's not diagonalizable. Okay. Nilpotent strings in Jordan form. So no one will be able to apply the definition of nilpotent and degree of nilpotency. Matrix is nilpotent if some power is 0. Degree of nilpotency is the smallest power for which it's 0. All right, given a set of strings, find the Jordan form of a matrix. All right, we had some problems like that in the last homework assignment. If I can show you what I'm talking about. All right, for instance, here's a set of strings. 1, 2, 3, 4, 5 strings. From this set of 5 strings, we can derive the Jordan form of this matrix. Right? T minus 2, that means that this is a Jordan block with diagonal entries 2. The Jordan block has size 3. Right? So that's going to be a 3 by 3 block with 1's on the subdiagonal, 2's on the diagonal. Here it is right here. Notice there are zeros below and zeros to the right. No other non-zero entries in those rows or columns. This here also tells me that this is a Jordan block with eigenvalue 2. With diagonal entries 2. It's also size 3. That's this Jordan block here. This is a Jordan block of size 2. That's the block here. And then these are 2 blocks of size 1. Notice that all the last vectors in the string are eigenvectors. This 0, 0, 1 is an eigenvector. You can verify that. This one here, 0, 0, 0, 0, 0, 1 is also an eigenvector. This is an eigenvector. These two are both eigenvectors. Right, the last vector in the string is always an eigenvector. All right, let's see. All right, given a 3 by 3 matrix, find the Jordan form and the Jordan basis. All right. And I will make another video about that shortly. Okay.